Hi and welcome. Today Group T will be presenting our group project using working model 2D software for KNJ2222 analysis of mechanics and machines. Here are the lists of team members: Ted Joffrey, Roel Hilson Untan, Devian Dickinson, Sharon Lee, and Valerie Ling.
This project responds to a critical global challenge, our rapidly aging population, and the urgent need for smarter mobility solutions. Traditional wheelchairs, while providing basic movement, are fundamentally limited. They are designed primarily for seated transport, often folding to deliver the comfort, safety, and functional independence users truly need. This lack of functionality is not just an inconvenience. The absence of essential features like adjustable height and standing support can lead to physical discomfort, poor circulation, and long-term health issues, while also increasing dependency on caregivers. These limitations highlight a clear and pressing need for an innovative wheelchair design that doesn't just move people but actively support their mobility, health, and overall well-being. To bridge this gap, our objective is clear: to design and stimulate a next-generation multifunctional wheelchair using working model 2D. Our focus is squarely on mechanical performance, ensuring structural stability, analyzing load distribution, and validating the safe operation of each innovative function. The design integrates key systems like adjustable height and assisted standing to enhance accessibility, comfort, and user autonomy. In the term of scope, the phase is dedicated to conceptual mechanical design and stimulation. Electrical system control and manufacturing are beyond our current scope, meaning all results are based on idealizing stimulation model. Ultimately, this project is about more than mechanics. By leveraging engineering stimulation, we aim to transform the conventional wheelchair into an integrated platform for health and independence. This work directly supports United Nations Sustainable Development Goal 9, which is SDG 9, Industry, Innovation, and Infrastructure, demonstrating how digital engineering and purposeful innovation can strengthen healthcare infrastructure and tangibly improve life. Now let's explore the core of our design concept. Our proposed wheelchair integrates adjustable height and assisted standing into a single, cohesive mechanical system. This transforms it from a passive transport device into an active postural support platform. The adjustable height mechanism is powered by an electromechanical linear actuator, enabling smooth control vertical movement while maintaining balance and structural integrity. Assisted standing is achieved through a coordinated mechanical linkage system. This mechanism provides gradual supported transition from a seated to standing position, enhancing safety and reducing reliance on caregivers. We have also incorporated a reclining seat mechanism for enhancing comfort during prolonged use. Every moving part is anchored to a reinforced frame, ensuring stability, safety, and reliability throughout all operations. In essence, our design does not just add features, it reimagines the wheelchairs as an integrated platform that promotes health, independence, and user dignity.
The main innovation of this multifunctional wheelchair does not lie in a single feature, but in the system-level integration of multiple mechanisms within one stable chassis. Unlike conventional wheelchairs that serve only a passive transport device, this design combines adjustable height and assistance standing into a unified mechanical system. A key innovative aspect in this dual-function lift system where the same lifting structure is used for both vertical seat adjustment and standing assistance. This improves functional efficiency while reducing mechanical complexity and redundancy. By directly addressing user dependency, limited accessibility, and the negative health effect associated with prolonged sitting, the wheelchair is transformed into an active health and autonomy support platform. The standing function enables weight-bearing activities, promote blood circulation, and help reduce muscle atrophy and joint stiffness, particularly among elderly users. Overall, this integrated and user-centric approach represents a significant advancement in assistive mobility design and aligns with the principle of innovation and sustainable infrastructure development outlined in United Nations Sustainable Development Goal 9.
Next is the kinematic diagram for the reclining mechanism of the wheelchair that we're presenting. Based on the kinematic diagram shown, there is two fixed joint that is present that ensures the seat remain at place during reclining. This two fixed joint is connected to both link 4 and link 8 that act as a support for the seat. This prevents the seat from breaking down and able to withstand the weight of the user. Next, the seat backrest and leg rest is modeled as rigid links. This is further supported by pin joints that allow for controlled rotational motion between the links. Last but not least, key slot joint and actuator acts as linear joint for the reclining seat. The key slot joint specifically allows for the backrest to withstand the weight of the user and prevent it from collapsing whenever it's going to recline. And the actuator acts as a push or pull for the backrest and leg rest to be able to allow it to go for the recline motion as intended. Now, for the link, joint, and motion control section, I'll be explaining deeper regarding the links, the joints, the key slot joint that we use, and the actuator. For the links, back seat or backrest, seat, and leg rest act as a supporting link to distribute the user's load across the frame. Meanwhile, link 4 and link 8 act as a support for the seat. Next is the joints. Now for pin joint allows for rotational motion while still keeping the reclining seat in place. Linear and fixed joint is also used by the actuator and link 4 and 8 respectively. Moving on to the key slot joint, the key slot joint is to limit and prevent a sudden recline motion when reclining. This is to ensure that the user remains comfortable and ensures their safety. Last but not least, the actuator. The actuator acts as the push and pull mechanism that allows for the backrest and leg rest to recline and incline. Now, moving on to the working model 2D setup. As shown in the picture, this is how our team sets up our working model 2D. The kinematic diagram that we've drawn previously have been translated into a 2D simulation model. The rigid body properties have been assigned to each component based on their colors respectively. The joint constraints have been implemented to match real behavior. This is to ensure that the result is as realistic and as close as possible to that we wanted. The actuator inputs have also applied control motion sequence. This is to ensure that the actuator we use is not just a random value and is a calculated and safe value that is able to be used by the elderly. Last but not least, the simulation time and step size have been selected for stability. The simulation period that we've chosen is specifically for a situation used by the given question. Now I'll be explaining the equator input. The equator motion that controlled is using displacement input. So based on the table on the left side of the screen, as you can see, it is a time against displacement table. While this is a simplified version of the table of time displacement, you can see the pattern that we chose the time taken to be 0 to 10 seconds with a displacement maximum of 0.032. The gradual extension applied is to avoid sudden movement, and the maximum equator displacement is set to 0.032. The symmetric extension and retraction profile has been used. What this means is both the leg rest and the backrest is able to function simultaneously and based on the same table and the same value. However, they can also be used separately according to the user's preference. This design is to ensure a smooth and safe reclining motion and to prevent a sudden movement in motion whenever they use the reclining feature. Now, moving on to the velocity analysis, the equator velocity is estimated from displacement data. However, we can also read the velocity value from the video on the right. The average equator speed is around 7 mm per second, and the rear wheel is driven at angular velocity of 1 radian per second. This value is specifically chosen because this is the estimated value of an elderly person pushing someone, that is, pushing a wheelchair with a person sitting in it. The corresponding linear speed is around 0.3 meter per second, and the motion of the wheelchair is classified as slow, controlled, and safe to be used. First is the reclining seat. The smooth reclining and incline motion is observed throughout the whole simulation. There is no sudden angular displacement happen during the backrest movement. The leg rest extends and retracts in a controlled manner. Same goes for the backrest. The movement of the equator is based upon the value of the time displacement table as explained previously. Lastly is the wheelchair itself. Based on the video that will be showcased in the next slide, smooth reclining motion occurs while the wheelchair is in motion and is observed throughout the whole simulation. There is also no sudden angular displacement during backrest movement. This shows that our wheelchair is able to perform using the reclining mechanism that we have created beforehand. The value of rotation of motor, and which acts as the dummy for a person pushing the wheelchair, is also indicated in the video as well. Last but not least, there is no tipping or balancing issue shown by the wheelchair during motion. The next slide is our AutoCAD 3D drawing for the whole 3D drawing. And this slide showcases our AutoCAD drawing in orthogonal form.
Here we have two different modes of the wheelchair. On the left is the normal mode, while on the right is the reclining mode, resulting from our modification. The materials used were wooden sticks, thread, cardboard, metal wire, superglue, and paper. The wooden sticks were used as the frame of the wheelchair model, while the threads and metal wire were used to secure the joints. Cardboard was used to form the wheel and the cushion.
Moving on to the alignment with SDG 9, the Sustainable Development Goals emphasize social inclusion and equal access to opportunities, especially for stigmatized groups such as elderly people and persons with disabilities. Usually, they have limited access to services, and assistive devices often leads to poorer health, education, and economic participation. Hence, we have come out with our own innovation of wheelchair. Our wheelchair is designed to address these challenges by improving the mobility and independence of the disabled person. It features an adjustable backrest, adjustable height system, leg rest, and reclining mechanism, which applies mechanical design and kinematic principles to meet the user needs. This wheelchair also supports inclusive use across healthcare, residential, and public environments while promoting scalable and standardized manufacturing. By enhancing accessibility and healthcare infrastructure, our design aligns with SDG 9, which is industry, innovation, and infrastructure, contributing to a more inclusive and resilient society while supporting the SDG 9. For the recommendation part, we have introduced a reclining mechanism to reduce back pain and improve comfort during prolonged sitting on the wheelchair. So we maintain the adjustable backrest, leg rest, height adjustment, and assisted standing to enhance posture, blood circulation, and neck support of the user. So we decided to do some improvement on the wheelchair by improving the portability of the wheelchair by developing a more foldable and lightweight design for easier transportation into the standard vehicles if you would like to bring it anywhere with you in the future. Other than that, we will also like to explore the integration of a robotic arm on the wheelchair to help elderly and disabled users to reach higher objects in the futures. However, this is a little bit harder to achieve because we need to consider the design complexity and the cost because advanced mechanisms and additional linkages required for the robotic arms may increase our production costs and the system sophistication.
In conclusion, this project focuses on the mechanical design of a multifunctional wheelchair that improve user comfort, safety, and independence. Unlike conventional wheelchair, the proposed design integrates an adjustable head system, assisted standing support, and reclining seat within one stable structure. The adjustable height mechanism allows safer transfer and better accessibility, while the standing support system helps reduce health issues caused by prolonged sitting, such as poor circulation and muscle stiffness. The reclining mechanism further improves comfort by allowing users to adjust their posture during long period of use. The mechanism were analyzed using working model 2D, and the simulation results show smooth motion and stable operation under ideal condition. Overall, this design demonstrates how mechanical integration and kinematic analysis can be applied to improve assistive mobility device and support innovation in line with Sustainable Development Goals 9.